Now let's take a look at isobaric changes. Isobaric means constant pressure. Now looking at the pressure line, what that means is we're going to be moving across like this without changing our pressure, either up or down. An isobaric expansion means the volume is going to get bigger while the pressure remains the same. So here's point 1, here's our starting point, here's our ending point, and our process is an increase in volume from this place to this place. We're not staying at the same temperature. Notice that we're shifting across two different isotherms. Here's one temperature, here's a different temperature. Looking at this physically, this is an isobaric change. This is an expansion. And what happened here was, well, there was definitely work being done here by the system on the surroundings. So that's a loss in internal energy. Look what happens, though. Volume increases. And here's what we know from Charles's law. Volume is directly proportional to temperature. So if the volume got bigger, well, the temperature would also have to have gotten bigger. How could the temperature have increased if these particles are losing energy through work? The only way that's possible is if that energy is replaced by some Q. Now, the temperature has to go up to make the volume go up. So the Q here has got to be bigger than the work. In an isothermal expansion, Q matched work. Here, Q has got to be greater than the work in order to make Charles's law not be violated. The graph also shows this. We moved to a higher isotherm. Our starting temperature was low. Our ending temperature was higher as we moved across this graph. Here's what the schematic diagram might look like for an isobaric expansion. Our system has a certain amount of energy before. Energy is lost through the process of expansion in work. Energy is gained by the process through heat to bring the temperature back up and then increase it to allow a volume change. And Q had to be bigger than W to get the temperature to rise. Well, if Q is bigger than W, then that means more energy went into the system than came out of it. So that means delta E is a positive number. So afterwards, we have E, whatever we started with, plus a positive change in energy. So we'll have more energy stored in the system afterwards than we did before in an isobaric expansion. An isobaric compression, well, we can easily imagine that it's just the opposite. You start at some point here at the high temp, point number 1, let's say, and you move without changing pressure to a lower isotherm, T low, and that's position 2. Physically, this is what this looks like. You've moved the particles into a smaller space by pushing on the piston, so the surroundings have definitely done work on the gas. That means the temperature would have to go up, but Boyle's law says when the volume goes down, the temperature also has to go down. So that means some energy has to escape from this process through Q. And the Q here has got to be bigger than the amount of work. Otherwise, the temperature is going to rise. We want the temperature to, in fact, fall. So looking at our schematic diagram for an isobaric contraction or compression, here's our initial system energy. The process involves energy going in through work from the surroundings, and then a greater amount of energy going out through heat in order to drop the temperature, not allow it to either stay the same or go up. So since the Q is bigger than the W here, and Q is out and W is in, that means more energy leaves the system than enters the system. So in this case, delta E is a negative number. There's a loss in internal energy. So E minus a certain amount of energy is how much is in the system afterwards. So after this compression, isobaric compression, the system has less energy stored in it than it did before. Let's look at isochoric changes next. These can't be compressions or expansions because isochoric, by definition, means the change in volume has to be 0. There's no change in volume. Looking at the volume scale, that means what we're doing here in these kinds of changes is we're following a vertical line. Now, an isochoric pressure increase means we'd be starting here and we'd be ending here, going upwards on that straight line from position 1 to position 2. Now let's think about what this means in terms of work. Work, remember, is defined as P times delta V. It's actually negative P times delta V to make the sign convention work out. Now, if there's no volume change, well, that means there's no work done here. So in an isochoric change, there's no energy exchange through work. Any energy exchange that does happen has got to be happening through heat, through Q. Well, there has to be an exchange because we're starting at a low isotherm and we're going to a higher temperature. The only way we're going to get there is by adding energy, and that energy can't come through work, so it's got to come through heat. So here's our schematic diagram. The system before has energy E. Work, well, there is no possible work to go into or out of this system because there's no volume change. However, we know that the temperature has got to go up for this to happen. So that means Q is entering this system. So Q is positive, work is 0, so the change in internal energy is Q plus W, and that means that's going to be positive. So there's an increase in internal energy as we increase the pressure isochorically. So after we've added a certain amount of energy, looking at an isochoric pressure decrease, well, that would mean we're starting at a high temp and we're moving towards the low isotherm. So there's a decrease in pressure without a change in volume. This is supposed to be a vertical line here from state 1 to state 2. Again, work is nothing. Can't have any work if there's no change in volume. But we're definitely losing energy because the temperature is dropping, so that means we must have lost that energy through heating. Q is negative. So back to our schematic for this process, for an isochoric pressure decrease, our original system energy shows no change through the work. You can't have work going in, you can't have work going out, it's not possible because it's constant volume. However, we move to a lower isotherm, so that means we must have lost energy somehow, and that would have to be through Q, because work and heat are the only two ways we can lose energy. So for this system, work is nothing. For this change, work is 0. Q is going to be a negative number. We've lost energy. The system has lost energy. And so that means delta E, which is Q plus W, is going to be a negative number. So after this change, after an isochoric pressure decrease, the system has lost a certain amount of energy, delta E. There's less energy stored in it than there was before. The last type of process we're going to look at is adiabatic changes. Here's what adiabatic means. There's no heat transfer. In other words, Q is equal to 0. There are a couple of reasons that this would happen. One would be perfect insulation, or really good insulation if you're working fast. Insulation can restrict heat transfer, and so that means Q would not be possible. The other reason that this could happen is speed. And this is where we see this happening in real-life situations. Lots of real engines, like gasoline engines or diesel engines, exhibit this process, this adiabatic change, just because the process happens so fast that there's no time for heat flow to take place. And so before heat could leak out of the system, it's already on to some new step in the process. So adiabatic changes are really good models for some things that do happen in real life. Let's look at an adiabatic expansion. Now remember, it's possible for work to be done here, but it's not possible for Q. So work is definitely being done. The system is moving the piston out. So there's a loss in energy by the system through work. That can't be made up by heat. That's not possible because this is adiabatic, and by definition that means no heat flow. Well, these particles have lost energy because they've collided with the piston and rebounded with less energy. That can't be made up through heat, and so what that means is the total internal energy of the system is actually dropping. So the temperature will go down in adiabatic expansion. Looking at an adiabatic expansion graphically, two things that we have to keep in mind. One is that the pressure is definitely dropping. So we're going from some point up here to some point down here. The other thing that we got to keep in mind is that the temperature is definitely dropping because the heat can't make up for the work. Now, it's a real expansion, so that means we're not doing one of these isochoric things where we're going straight down. But it's also not isothermal where we're following the isotherm. So that means our ending point is somewhere down here. And we get this sort of a curved line going from point A, or point 1, to point 2. We're changing temperature. We went from a high temp, a high isotherm, to a low one. But we didn't do it isochorically. It was somewhere in between. That's adiabatic expansion. Where is that line exactly? Well, there are ways to figure it out, but we don't have to worry about it in this class. So here's a schematic diagram for an adiabatic change. The system starts out with energy E, Q, in or out, not possible. Now, in the expansion, here's what we know. The system is doing work on the surroundings. So the process causes a loss of energy through working from the system. Afterwards, energy is decreasing. That's because Q is 0, but work is negative. The system is doing work on the surroundings, so there's an energy loss through work. So delta E is going to be a negative number. After an adiabatic expansion, the system doesn't have as much energy stored in it as it did before. For those of you who are motorheads and understand how a gasoline engine works, this is the expansion process after the explosion. You're taking the energy that was stored in there during the explosion, and you're turning that into work, and there's definitely a temperature. Thinking about an adiabatic compression is it's just sort of the reverse. So you're starting now at the low temp, and you're moving to the higher isotherm, but you're not doing it isochorically. It's following this curved path, going from point 1, starting point, to point 2 on the higher isotherm. Thinking about an adiabatic compression in the schematic diagram, you start out with some energy E. The system is definitely doing work on the surroundings because it's compressing the particles, but Q can't either move energy in or out. The process of heating is not allowed here, and so with Q equal to 0 and work being a positive number, delta E is also a positive number. It means that you're going to have an increase in internal energy of the system during this compression. In fact, that means the temperature goes up. Those of you who understand how a diesel engine works, this is what happens when it gets so hot in there that it actually ignites the diesel fuel without a spark plug.